problem number 3, it wants us to determine for the following system, given the signal and noise input wattage levels, find the signal to noise in decibels, signal to noise out in decibel, then the noise ratio and noise factor. So, to start off, we need to make sure we have both the decibel quantity and the ratio quantity for the powers involved with this system. So first we can see that for the device we were given the power in dB and the noise in dBm. So we can convert those to ratios and watts just so we have them at our disposal. So let's go ahead and do that. So the gain ratio for this device, we're just converting to the ratio from the dB. So 3162.3, and we end up using that quantity later, most likely. And for the noise of the device, it is in dBm, so we have the 1 milliwatt reference. And just plug in the dBm value that we were given for our device off of the figure, and we end up with 158.49 picowatt. All right, so now we have some quantities we may need to work with. So let's go ahead and look at part A. We want to find the signal to noise input ratio in dB. So to find that, the signal to noise in dB, it's just going to be an equation given in your book, and you can find that as equation 3.6, but it's just 10 log of the power of the signal over the power of the noise. And both of those quantities are actually given in the problem to us. We have the signal input power and the noise input power. So we can plug those here. The 100 picowatt and 20 femtowatt is what we're plugging in there. So let's go ahead and do that. Just 10 log there's our 100 picowatt, 20 femtowatt, and that's 10 to the minus 15. We don't use it too frequently. And plug all that in to find the ratio of 36.99 dB. For part A, that's our incoming signal noise ratio. We now want our output signal noise ratio in dB. So for part B, we're trying to find signal noise out in dB. For that, we also have an equation we can refer to in the book. It's equation 3.13. So we have our signal out over noise out, or incorporating the device properties, we have the gain ratio times signal in divided by the gain ratio times noise in plus the noise of the device. So again, that's equation 3.13 that we're plugging into. So let's go ahead and do that. That'll get you 10 log of, here's where we're plugging in many of those factors. One will be the gain ratio of our device, which we calculated earlier, which is 3162.3 times our signal coming in, 100 e to the minus 12, divided by, again, the gain ratio times the noise in, and plus the noise of the device, which we have here, this 158. So 162.3 times the noise in, which is 20 femtowatt. And plus what we calculated here, the 158.49. Picowatt, so that's e to the minus 12. Just barely fits in frame there. And so when we solve that out, let's come back over to this side so we can see our solution. We can see that our signal noise output ratio is 31.54 dB. So 31.54 dB for our answer for part B. Now part C wanted us to determine our NR and NF, our noise ratio and noise factor. So let's clear some room for that. We'll have to use some of those numbers we just calculated to find those out though. So for part C, we'll start with the NF, the noise figure. We just take our signal in dB minus the signal out in dB, which you can see in equation 3.10. So it's just signal noise in dB minus signal noise out dB. Those are the two quantities we just solved for in part A and part B. So one minus the other, 36.99 minus 31.54, and we would get 5.45 dB. And then for the ratio of that, you can see in your booklet that they just have the 10 log relationship moving between dB and our ratio. So going in the opposite direction, we just take 10 raised to the 5.45 to convert from dB to our ratio, which is 3.51 for our NR, our ratio for part C. So that was it for problem number 3.